So for those of you here last time, we featured one of our young scientists, Kevin Schlafman, and I pointed out that the last two lectures were featuring two of our young scientists. So today you get to hear from Katie, who's an amazing Hubble Fellow. The Hubble Fellowship is a national program in the US. It's very competitive. These are really some of the top jobs you can get in astronomy, and it's named after Edwin Hubble, appropriately, a Carnegie astronomer. And it's very appropriate for Katie because she works on the topic that Hubble actually established, that is, the study of galaxies. Hubble was the first person to demonstrate that our own Milky Way was one of we now know billions, trillions of galaxies in the universe. And ever since Hubble's discoveries in the 1920s about galaxies, Carnegie has really played a leading role in trying to understand how the universe of galaxies that we see came to be. This is a really, really interesting topic, and one that we continue to do today. And Katie is the latest young astronomer in a line of many to work on this very exciting topic. So help me welcome Katie to the stage.
So thank you, John, for giving me this extraordinary opportunity to speak to you all today about galaxies. When I got asked to do this talk, I quickly said yes and thought it was very exciting and gave a title of my talk, Secret Lives of Galaxies. And then the printer presses worked and the brochures went out, and I said, I'm not sure if I like that title. So I decided that here I was going to unveil a new title for you all. Sure, we can talk about the secret lives of galaxies, but I think I'd rather talk about 100 ways to die in the universe. Murder, suicide, and zombies in the life and death of galaxies. So before we start, John gave a little bit of an introduction to me. I figured I'd give you a little bit more of a personal one. So I was born in Michigan, got my degree at the University of Michigan, go blue. Trekked across the country to the University of California at Berkeley, where I got my PhD, and then decided I really liked California. So instead of moving anywhere else, I moved south, where I did a postdoc at Caltech and at the Infrared Processing and Analysis Center. Decided I still really liked California, and ended up with the opportunity to work at Carnegie Science. So when I refer to myself, I call myself a galactic archaeologist. What do I mean by that? It means that I study galaxies. I study modern-day galaxies where I am searching for imprints of past interactions. It means that I am looking carefully at all of the galaxies in the sky to find those few galaxies that are actually changing and dying right now. And that means that I am using the universe as a time machine to try to find galaxies that are dying 10 billion years ago. I come in a long line of people who do this. So Charles Messier was a comet hunter by trade. That's what he liked to do. He wanted to find all the comets in the sky because, just like today, it turns out comets get named after you if you find them first. Charles knew that. He really wanted them. But he started noticing something annoying, and that was that he would go and he'd classify things, and he'd find things that looked fuzzy like a comet, and the darn thing would just stay in the same place in the sky. So he started calling those nebulae. And ironically, Charles was actually pretty good at finding comets. He found 13. But we don't remember Charles Messier for his 13 comets. We remember him for the Messier catalog, which is actually a catalog of objects in the sky, extended objects in the sky, that you can see either with your naked eye or you can see with binoculars. Going beyond this, again, I'm lucky enough that my office sits kitty corner from Edwin Hubble's old office. Sorry, there are no ghost stories. I wish to. So Edwin took this 10, 15 steps further. Because what he did was he started looking at these nebulae, which we were not sure were inside of the Milky Way or outside of the Milky Way, and he said, I think the universe is much grander than just the Milky Way. And believe it, at the time that he was doing this was a big debate. People were not sure. And what he did was he looked specifically at M31, Andromeda Galaxy, and he looked for stars inside of the Andromeda Galaxy that he would be able to figure out how far away they were because they had some very predictable brightness. And what you see here, by the way, Hubble's actual handwriting, is he found one right there. It was a Cepheid variable. I'm not going to go into this. There are some extraordinary scientists at Carnegie who work on this. And he was able to show for the first time that the Andromeda Galaxy was a completely separate galaxy from the Milky Way. It wasn't just some little blob inside of the Milky Way. It was outside of it. That's not actually why I care about Edwin, though. So I'll point out, this is actually Edwin Hubble working on the 100-inch at Mount Wilson, which you can actually go visit. And I believe if you pay some certain amount of money, they're actually retrofitting this so that you can actually view through an eyepiece the same glass that Edwin Hubble worked on 100 years ago. What I care about is actually that not only was he finding that these objects were cosmological, that is, they were not just inside of the Milky Way. Edwin Hubble also created a classification for galaxies that we astronomers, and probably not just astronomers, but laymen too, know as the Hubble sequence. So, what I mean when I say Hubble sequence, the classification employed is based on the forms of the photographic images. Blah, 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 irregular. The sequence is composed of two sections, the elliptical nebulae and the spirals, which merge into one another. And I'll point out this is actually Edwin Hubble sitting in the prime focus of the 200-inch at Palomar. So what Edwin Hubble did was not only did he prove that things like Andromeda were outside of the Milky Way, he actually was also able to classify those galaxies and put those galaxies into a sequence. And unfortunately, when he did this back in the day, he thought the sequence worked this way, that the ellipticals became spirals. Turns out in modern times we know that it was the opposite. So even if you're Edwin Hubble, you make a mistake. Take that too when you have to take your SAT. So what are these types? Over here, you have spirals, and over here you have early type galaxies. A typical spiral is disky. It has spiral structure, it's a spiral. It is blue in color, and it's star forming. Early types are a little bit different. There are actually two types of early type galaxies: lenticulars and S0s, and ellipticals. The thing about early type galaxies that puts them into a class is that they lack spiral structure. In science speak, we would say they'd have a smooth light profile. Basically, what you're looking for is no discontinuous spiral structure seen. Usually, they also ellipticals are ellipsoidal, lenticulars are disky. They tend to be red in color, and they tend not to be star forming. So, in summary, here we go. The thing that's important is that 77% of the galaxies in the sky are spirals, and the rest are ellipticals, with, again, Edwin Hubble explaining to us that some of them are also irregulars. The thing that separates these galaxies, besides, again, these morphological changes, is star formation. Why is it that when we see spiral galaxies, they look blue, and when we see elliptical or lenticular galaxies, they look red? It actually comes down to how stars form and how star formation works. Unfortunately for the big blue stars, they live like rock stars. They live hard, they live bright, and they die fast. So what you're seeing here is a couple of very massive stars. Turns out when you're massive, you have very high temperatures, and that actually turns your colors blue. It also means that your light in your galaxy, if you have some stars forming, are overwhelmed by these blue stars. If you wait a little while, no more of the blue stars are there, maybe they've exploded in supernova, hopefully they haven't exploded in supernova near us, what you find is that the less massive stars are redder in color, they live much steadier lives, and they're cooler. So, When you look at a galaxy, what you're looking at is a huge summation of all the stars in that galaxy. So a galaxy that is blue is a galaxy that has a lot of star formation because all of those rock star stars are dominating the light. And a galaxy that is red has stopped its star formation because those faint stars, it takes them a very long time to be bright enough to be the dominant thing you see when you look at a galaxy. How do we measure star formation? How do observers and astronomers actually get a sense of what star formation is? We start with a picture. So what I'm actually showing you here is a real star-forming blob near the center of the galaxy. And what I'm showing you here, besides this, which is the Pleiades, is me making a cartoon. So when these young stars are forming, turns out they're really hot. They're not just blue, they are ultraviolet. But because of where they need to form, they are a lot of times obscured by blobs of gas and dust. So what you have is once in a while, some of these hot young photons make it out of this hot, newly formed stellar cluster, but a lot of them actually get absorbed. And either they get absorbed and then they get re-radiated by the gas that has absorbed them, like this, where the hydrogen is actually re-radiating that hot energy. Did any of you guys remember doing arc lamps in chemistry? Turns out this is a star doing the same thing. Or they get re-radiated by dust. So the dust grains actually take care of it too. What that means is that we have multiple different ways to trace star formation. We have ultraviolet light, we have re-emitted dust, and we have H2. Or we have actually, H2 would be, we have hydrogen lines. Problem is, ultraviolet is ultraviolet, the dust is actually in the far infrared, and your and my eyeballs only work at optical. So when we look at the sky, all we see is this. We see the Milky Way. And I was 2 weeks ago down in Chile, where I got to see, you get to see the part in the north. I also got to see the part in the south. But that's the thing, is yes, in Edwin Hubble's time, that was basically all he got to look at, was look at the optical light. Astronomy's come a long way. So we now can look at pretty much every wavelength you can think of, from very, very low frequency radio waves, all the way up to gamma rays. And to give you an idea, this is X-rays are what they use to give you, well, they're called X-rays, to check your teeth. I get lots of those, unfortunately. But this means that we have a whole lot more information now than Edwin Hubble did when we started this work looking at galaxies. So, for instance, optical light traces this big black blob, which is actually probably the site of dust. I showed you dust in the last schematic. Near infrared is actually telling you where the stars are because you don't have quite as much obscuration in near infrared. Mid-infrared and infrared are actually probably showing you, again, where the dust is. And finally, the molecular hydrogen, which you can see right here, is showing you the placement of the actual star-forming fuel. So if I were to think about where is the star-forming fuel and where are the stars forming, and I only give myself 2 things to look at, I will readily admit I'm a radio astronomer, which is why I picked these 2. What you should be able to see is that this band seems to be sort of in the same place as where this is at its peak. So how do we study all of these different wavelengths? Well, we use a lot of telescopes. I'm not going to lie, this is a perk of the job. So we use telescopes in space. Chandra is an X-ray telescope that is looking at the very energetic particles. Herschel was a far infrared telescope looking at that dust. Spitzer is a near-infrared and mid-infrared telescope, also looking at dust, but looking at where the stars are. And again, I think we all know Hubble, not just the person, the telescope, that we needed to go into outer space and put glasses on. But we also can do a huge amount of stuff from the ground, including from this telescope, which is in the Canary Islands, the SDSS, but in particular, 2 that are at Las Campanas Observatory, which is run by Carnegie, Magellan, and the DuPont. And then finally, this row, which is maybe not my favorite row now that I've gotten to go down and use the Carnegie telescopes, radio telescopes. So how do we find star formation? Do any of you know what galaxy this is? Did I hear someone say whirlpool? I will pretend, I swear I heard someone say whirlpool, but we're going to pretend someone said whirlpool. This is the Whirlpool galaxy looking in the ultraviolet. And GALAX was actually a space telescope that could look in the ultraviolet. So again, ultraviolet tests finding out where those young rock star stars are. Turns out H alpha, which is again coming from this hydrogen atom, is right here. This is actually telling you the very sites of the most massive stars. And then when you look at it with the far infrared, you can see the dust. Again, tracing very similar places. How do we find the star-forming fuel? So first off, here is a composite image from the Hubble Space Telescope, again of the Whirlpool galaxy, where now you're seeing that dust structure again. This is what happens when you look at it just for the dust with Spitzer. And here's where the star-forming fuel is, the molecular gas. The way the conditions that are able to form stars require gas that is cold and is dense. And it turns out hydrogen, which is the first and most abundant element in our universe. It was the one that was made by the universe, not by stars. Looks like this when it's cold and dense. Turns out the atomic hydrogen actually bonds together and becomes molecular hydrogen. That's great. If we could find where we find those kinds of molecules, we would be able to find star formation. There's a problem with hydrogen, though. It turns out the way that hydrogen radiates is extremely weak, despite being very, very abundant. And so unfortunately, plan A, look for hydrogen, didn't work for astronomers, and we had to be clever and think of a different thing we could do. Turns out there's another element, one you don't want in your house, but one for astronomers is really, really convenient. That is actually carbon monoxide. It turns out carbon monoxide forms with exactly the same conditions, cold, dense gas, that hydrogen forms in. On top of it, some of the first elements that stars form after they have collapsed and become stars is carbon and is oxygen. That means that even in very, very young in the universe regions where you have not had a lot of stars form, the very first things that are coming out of those first stars is carbon and oxygen. On top of it, because of the fact that this is a lopsided molecule instead of a symmetric molecule, this molecule is very bright when it radiates, so it's really easy to find. So what I'm showing you down here when I said this was molecular hydrogen, it's a little fib. It's not quite molecular hydrogen, it's actually CO. The way we observe CO is with radio telescopes. What I'm showing you here is an all-night time lapse from the Combined Array for Research in Millimeter Astronomy, or CARMA, taken in the Sierra Nevadas. This was actually just up, if you've ever been to Mammoth Lakes, this was about an hour south of there. And what they do is every single one of these dishes, as you can see, is moving in congress with each other. That's because these dishes are actually combined, which means that we're actually able to get an image from them. Unfortunately for us, the funding fell through and CARMA had to be shut down. But the good news is there are other radio telescopes like that, including the Atacama Large Millimeter Array in the Atacama Desert in Chile, and Plateau de Beure, which is actually near Grenoble in France. So why do we care about this? Why am I talking to you about how we observe star formation? How do we observe star-forming fuel? It's because of the question I personally had. I showed in my title, just 100 Ways to Die in the Universe. I care about how galaxies go from this kind of galaxy to that kind of galaxy. Because in the modern universe, that is, in present day, when you go from being a bright, vibrant rock star forming spiral to a red and dead elliptical, you're stuck. You're not going to get to go back. And unfortunately for us, and I'm previewing a little forward here, this is probably something, someday, the Milky Way is going to look like that. So it's really important to understand ways that this can happen. And again, I also maybe told a little fib in my first slide by saying 100 ways to die in the galaxy, or the universe. But I'm only going to describe 5. So let's start with death by strangulation. I have a pun for all of them. Falling into a cluster. A cluster is a large grouping of galaxies that are all sitting in a common envelope of hot gas. It turns out, because gravity attracts things together, clusters are just a natural consequence of that. There are places in our universe that were overdense when they were forming. Lots of galaxies were there, and the galaxies, attracted to each other through gravity, collapsed and formed. And it turns out they also got a common envelope of gas. So let's throw a little galaxy into the cluster gas. This is the galaxy, and the dark blue will be gas. Well, what ends up happening is when that galaxy's gas hits the cluster gas, the pressure actually ends up stripping the gas out of the system. Bye-bye star-forming gas. That means, as the galaxy gets further into the cluster, it has lost all ability to replenish its star-forming fuel, and it starts to die a little bit. So what you can see, number 1, the gas is now a lot smaller. The galaxy is now green because, again, faint little red stars, blue rock star stars, because your blue rock star stars are starting to die out. That means the color of your galaxy is red plus slightly fewer blue stars plus slightly fewer blue stars, which makes the galaxy look green. And then finally, womp. You lose all your gas, you lose all your ability to form stars, you die and you become red and dead. And just to show you that when I say that this happens, it's real, take a look at this galaxy. See these structures right here? This is actually the stripping of the gas out of the galaxy, which astronomers call ram pressure stripping. So what I'm showing you here is a cluster, Abell 2218. Now I want you to look really carefully at this cluster quickly, and I want you to tell me what kind of galaxies you see in that. Are they, I'm going to do a show of hands. Are they mostly spirals? Are they mostly elliptical and lenticulars? Yes. Most of the galaxies in here have been strangled. Therefore, most of the galaxies in clusters are red and dead. So that's your first way to die, be strangled. Second way to die, death by battle, which is mergers and interactions. This is actually probably the one that has the most, is the best computationally studied. So since 1970s, we've been able to actually make computer programs that take 2 disky galaxies, smush them together, and turn them into a red and dead galaxy. Technology has increased from here, and I'll point out that the simulation I'm showing you, this is not just an artist rendition movie. No, this is a simulation that Phil Hopkins, a professor at Caltech, stuck physics into. Shows you what happens when 2 galaxies merge, and yes, we have observables on top of this. So first off, in the stars, for the most part, they kind of run right through each other. So even when, inevitably, we emerge with Andromeda, the solar system is not going to smash head-on into another star. Well, at least the chances are astronomically low. But what you can see is that as they smush together, first of all, you're seeing these bursts of star formation because you're driving the gas, you're compressing it, you're making it denser. That's making more stars. But also, take a look now. The end game certainly doesn't look like a disky galaxy anymore. It sure looks like an elliptical. So I did say that mergers kill galaxies. Inevitably, that means that 2 star-forming galaxies die and become a red and dead non-star-forming galaxy. Except then I told you that there's an explosion of star formation that takes place, and that is also true. So here are some images from Hubble Space Telescope of mergers. Let me show you why this is not in disagreement with my previous statement. When you look again at this simulation, Take a look on this side again is the same merger video I showed you before. But look over on this side at the gas and look carefully at where the cold gas is, where the warm gas is, and where the hot gas is. I hope you're seeing this. These two galaxies, you're starting to see that hot gas increase. You're starting to see that diffuse halo of hot gas forming as these two galaxies come together. You're also seeing now all of a sudden the gas is no longer in a single place. The gas is no longer in two individual disk galaxies. The gas is all sitting very, very close to the center. What that means is that you've now taken a merger, you've taken all this wonderful star-forming gas, and you've shoved it all into the middle. That's done a great job exploding star formation, but there's a problem. Something lurks in the nucleus of a galaxy. So what I'm showing here is a schematic from that beautiful video made on Keynote, so I apologize in advance. Two isolated disks have a first interaction. You have some stars form. At some point, they coalesce, and you have an explosion of star formation. But then you get to here. The gas is all sitting really close to the center, and galaxies all have supermassive black holes sitting in the center that are hungry. So what ends up happening in this schematic is actually that supermassive black hole now has access to all the rest of that star-forming gas, and it blows it out. So in the schematic, next, you blow the gas out of the system. No longer can this merged, vibrant, exploded of star formation thing form any more stars. The quasar turns on. Quasars basically being when the supermassive black hole actually gets the chance to eat. Turns out gravity is a really good way to turn on, to release energy. All of a sudden, you've now removed all of your star-forming fuel, and all the young stars have supernovated, exploded, gone away. So you get to a stage where because there's no more gas, you're now decaying. The stellar populations are aging. You become green again, or as in astronomy, we like to term post-starburst, and then finally, you become red and dead. Next, the death by melee. Compact groups. So I talked to you about clusters, which have this envelope of gas that is able to, by pressure, strip away the star-forming fuel in a galaxy. I've talked to you about mergers, whose interactions put the gas all into the very center of a galaxy, which then blows it all away from a quasar. Unfortunately for compact groups, they get the worst of both worlds. We are not only dealing with a set of systems that interact a lot, we're dealing with a set of systems that form a common envelope of gas. So when Paul Hickson did the work on Hickson compact groups, you can still get things named after you in astronomy. I haven't found my thing yet, but I'm looking. By compact group, we mean a small, relatively isolated system of typically 4 or 5 galaxies in close proximity to one another. The way Paul Hickson did this kind of sounds like something Edwin Hubble would do, frankly. He looked at plates, photographic plates of galaxies, and he looked for multiple galaxies that were really close by each other in space. And then he tested to see if their brightnesses were about the same, to tell you that the galaxies weren't just projected. I hope you can see that this finger and this finger are not close together, even though they look like they might be from your line of sight. He looked for them to be similar brightnesses to see if he could find groups of galaxies that were very compact. He found about 100 of them, and it turns out when we were able to go back and look at the spectra of those galaxies, we found that 92 of them were indeed compact groups. So compact groups tend to have a high fraction of dead galaxies. They tend to have tidal interactions, so think back a few slides on the death of clusters, those streams of material coming out of those galaxies. These things have them too. And they're high density and have lots of interactions. They're close together, and they're constantly jarring with one another. So my death schematic of compact groups. Some point, first they start in a loose association. Again, blue is the galaxy, dark blue is the gas. They get to a compact group phase where they're starting to interact with one another and are actually smashing into each other, heating their gas, et cetera, et cetera. They start dispersing their star-forming fuel. That is, their star-forming fuel, which originally was in the disks of the galaxies, was owned by those galaxies, now seems to be owned by the group. And they continue to interact and shock and heat up gas until they have a common envelope of gas that then becomes an X-ray envelope. And we actually think that compact groups are one of the ways you can form giant ellipticals that are not formed in clusters. And now we go back to the black hole. Eaten alive by a black hole, or AGN feedback. And this is actually one that I have a lot of fun with because this object was the mystery and the muse of my graduate education. So if you look at this galaxy, NGC 1266, I think what you would say is, do you think that this is a vibrant star-forming spiral? Or do you think this looks more like one of these lenticulars or ellipticals that I'm talking about? So who thinks that this is a star-forming spiral? You guys are good. Who thinks that this is red and dead? We thought that too, till we pointed Hubble at it. So number one, this is what an unphotoshopped image of Hubble looks like. Just so you know, doesn't always look perfect and beautiful like the Hubble heritage. You got to do some work to make it like that. This is what we would call science quality. So what you can see is when we were able to point Hubble at the center of this galaxy that by all means looked kind of red and dead, what we saw is that crazy stuff was happening in the center. In the center of this galaxy, there was a huge outflow coming out of exactly the point that we thought there to be a black hole. So we looked at it in molecular gas. As I said, I was a radio astronomer. Of course I'm going to point a radio telescope at it. What you can see here, this is what we got when we pointed one of these beautiful interferometers at this, Karma. Because, again, this is science quality, this is what these data mean. So this red lobe right here represented that star-forming fuel, that H2, flowing outward behind the nucleus. This yellow blob right here is the H2 that's still in the center, and I want to point out this tiny yellow blob is very, very small. This tiny yellow blob is, I have to do the math in my head, about 1,000 light years across. Just to give you some idea, we are in the Milky Way at about 24,000 light years. This is about a 1/24th of the distance between the center of the Milky Way and us. But that's a Milky Way mass worth of gas. So somehow this object has as much star-forming fuel as the Milky Way sitting in this tiny little region really close to that black cross, which I'm going to point out is the position of the black hole. And this blue blob right here is actually H2 flowing outward in front of the nucleus. Now this should be great. You have a whole lot of star-forming fuel that you should be able to form stars with. Maybe NGC 1266 has a chance to come back and no longer be that red and dead galaxy. Maybe it's the one that's going to come back across. Nope. No. Unfortunately, this outflow is pulling out 50 masses of the sun per year from this center. Turns out it can't form stars because there is so much energy sitting in that center, not only pulling gas out of the system completely, but it's keeping stars from being able to form because it turns out the gas can't get cold and dense if you constantly have a black hole throwing a jet through you. Sorry, NGC 1266. And it was great to get this object as a student. It was great and terrible. It was great because it's always fun to be lucky enough to be sitting on the forefront of a new discovery. It is terrible because if you're stubborn like me, you are unwilling to let this object go until you have understood it to the level you are happy with. And I will say, NGC 1266 and I have come to an agreement. I think I understand how it works. It's great. We've signed the divorce papers, and I'm trying to move on. Case studies are great, but they can't tell us about a population. NGC 1266 taught us about one object, NGC 1266. Problem is there a circle of life and death in galaxies that this one object just doesn't represent that exists? Have we found all the ways that galaxies can die? As I said in my title slide, 100 ways to die in the universe, and I'm giving you 5 of them. Does the star-forming fuel have to blow away? Does it always blow away? Can it still be sitting in a system, and that system still be doomed to be red and dead? How often is the black hole part of the killer scenario? I showed you that schematic for mergers. Is that right? Do we really need to put all the gas really close to the black hole so that the black hole serial killer can finish it off? Don't know. We know in NGC 1266 it is the case. We know in simulations that seems to work fairly well. We don't know if that is necessary. And finally, have we found all the ways galaxies have died since the beginning of time? An example, just because a guy today has heart disease probably doesn't mean that all the dinosaurs died because of heart disease. A galaxy today might not represent anything about a galaxy in the early universe because conditions were all completely different. So if you're an astronomer, what do? Well, you create an acronym. So NGC 1266 had 2 very interesting pieces of information in it, that don't usually go together. It had shocked ionized gas, that is, in the center. That outflow was burbling all the gas up, it was shocking the gas, and we could actually observe that that was going on in that center. And it had young, but not infant stars. So it was one of these green galaxies I showed you, not one of the red and dead, not one of these rock star galaxies, green. So we created an acronym and called it a shocked post-starburst galaxy, or a SPOG. And then we put NGC 1266 right in that class and said NGC 1266 is a SPOG, therefore this is a real thing. We did more than that. Using that special combination of shocked gas and young but not infant stars, we turned our attention to the Sloan Digital Sky Survey, which has about 1 million galaxies that we get to play with. By the way, it's public, in case you guys want to play with it yourselves. And we found about 1,000 new galaxies that could be these galactic zombies, could be these NGC 1266 dying galaxies. We don't say that they're all galaxies that the black hole is currently eating them alive. We don't say that they're all coming into clusters. They're not all in groups. They're not all in mergers. We're hoping there are things that are in this set of galaxies that we've never seen before, killing the galaxies. And just in case you're interested, because I believe in being public about our data, you can actually look at all 1,067 SPOGs at www.spogs.org. So, to the end, the dead and the walking dead of galaxy evolution, the ellipticals and the lenticulars, and this is the death by galaxy shape. Ellipticals and lenticulars grow so big that gas can't get back into them and start forming stars again. But they're also really interesting, because if you're looking for ways galaxies died, looking at a galaxy that's dead might still hold those imprints that that galactic archaeologist is interested in to figure out why they died. So I end here partially because I have kind of a fun little treat to our future for you. But after a galaxy merges, the H2, you just can't get enough molecular hydrogen and star-forming fuel to turn a galaxy back into a disk. And I mean, if you're in a cluster, you're SOL anyway, because in a cluster, you can't get the gas in the first place. And you kind of just slowly but surely fade, become redder and redder and redder. as you lose the last youngest set of stars. So we looked at about 250 of the local ellipticals and lenticulars, and what we found was that there were all sorts of ways that these galaxies died, many of which I've described to you today. Some of them died so long ago that we're still looking for what actually did the killing. I didn't mention minor mergers, which I guess we can call death by a million pinpricks. But you're kind of stuck. So what's going to become of us? The Milky Way and Andromeda, as I said, I previewed, are going to crash into one another. It's inevitable. It's gravity. In about 10 billion years. So what will become of the Earth and our solar system at that time? For instance, what if we were alive and were able to live for billions and billions of years to actually witness this? What would it look like from an Earthling's point of view? What would the sky look like? Have it, the death of the Milky Way and Andromeda. So I hope you now understand my title of my talk, which maybe isn't 100 ways, but it's 5 ways to die in the universe. Falling into a cluster, mergers, galaxy groups, black holes, and galaxy shapes. And I'm going to leave you with one piece of wisdom, what I like to call the observer's creed, as we ask ourselves, did we find all the ways that galaxies die? And just so you know, in an observer's head, there's only one answer. We need more data. Thank you all so much.
Solar system be theoretically thrown to the outskirts or thrown out
Oh, yes. Yes, sorry, sure. When Milkomeda is formed, is it possible that the solar system will either be thrown on a really eccentric orbit or thrown completely out of the system? And the answer is absolutely that could happen. Absolutely. If we are one of the unlucky stars, as we're coming into this whole new gravitational potential mess, we end up at just the wrong place, we can absolutely be slingshotted out. So we'd be able to watch as we're sort of slowly fading away as the galaxies merge.
Yeah, but at that time, the sun will be a faded, a burned out sun, right?
Oh yeah, we have bigger problems. We have much bigger problems than worrying about the merger of Andromeda and the Milky Way, including the sun is going to be burnt out, including it's going to be a white dwarf. There's probably going to be several supernovae that have gone off, that some, potentially we could even be in the line of sight of a gamma ray burst, which would be really bad.
But I also have a comment. You said the creed of astronomers, we need more data.
Observer.
If you ever go to law school, the answer to every question in law school is, it depends.
Actually, that's pretty true in astronomy, too. Yeah.
Nathan, go ahead. You have another one.
Okay. And also, just let's say that Milkomeda is formed before the sun gets burned out. Let's say, or at least we're in another galaxy. Theoretically, this is kind of a comfort, even though we'll all be dead and gone by then. Well, at least everybody in this room. Well, like if we get slingshotted out with the sun, and the rest of the solar system, I'm pretty sure we would be fine as long as the sun is there, because the sun is light. But what if we were separated somehow? What if the sun just didn't want to come along?
It would basically be the same as if the sun was a white dwarf. We'd be in big trouble, given that most of the energy we know how to harbor is in photons. For you, Nathan, I actually have a book recommendation from a friend of mine, Fred Adams. The book is called The 5 Ages of the Universe, which actually goes through what will happen to the universe, not just in 10 billion years, but in trillions and trillions of years when the only thing that is left is black holes. 5 Ages of the Universe.
If I'm not mistaken, isn't the isotope H2 deuterium?
Oh, that is a really good question. You're asking, is the isotope of H2 deuterium? This actually comes down to the difference between basically the nucleus of an atom and separate atoms. So H2, with a subscript, is when 2 hydrogen atoms, again, 1 proton in the center, chemically bond together. And deuterium is what happens when you have a proton and a neutron in the nucleus. I'd say it was a hydrogen atom, but it isn't. It's deuterium. It still has 1 proton and 1 electron, so it acts the same way as hydrogen, but it has that extra neutron in it. And deuterium is one of the things that was also formed in the early universe. I don't think that we know of any physical processes these days that can form deuterium, and so deuterium is one of those isotopes that is just decreasing slowly but surely as the universe goes on.
In these various galactic evolution scenarios that you presented, what are some of the differences that one would expect if the galaxies were dark matter rich as opposed to dark matter poor?
Yes. Also because I need to think about it. So the question was, in the multiple kinds of galaxy evolution scenarios that I'm presenting, what differences could we expect depending on whether or not the galaxy was dark matter rich or dark matter poor? And for those of you who don't know, dark matter is this excess mass that Vera Rubin, of all people, she's actually a Carnegie staff member in Washington, D.C. at DTM, found that doesn't interact with normal matter except gravitationally. Depending on what the dark matter, so if we're looking at the galaxy shapes, dark matter actually plays a huge, huge role. Turns out if you have a huge dark matter halo, which is what we call it, gas trying to get into that galaxy and filtering into that galaxy can't make it without superheating and no longer being able to cool. It turns out galaxies that have really, really big dark matter halos actually tend to die earlier on in the universe. Because again, of things like that, you have a really big, massive dark matter halo, you can't get gas down into the center to keep forming stars. There's way more, but that is the stuff that I can say that I know about, so that's where I will leave it for here.
Looking way into the future, outside of the local group, the distant galaxies will have accelerated to such velocities that they redshift out of our view. And so we won't be here, but how will that affect the Milky Way?
It won't. So the reason it won't affect Milkomeda is because we're all bound in the local group. We actually, quite honestly, like as we go further, it's very likely the Milky Way and the local group will end up in a cluster. But the reason it won't matter is because, yes, you're getting acceleration of the universe, but the objects are close enough to us right now that we feel this gravitational bond. Now, for the most part, I'd say that the sky would get darker, but it's not getting darker by much because, again, most of the stuff that we see is stars inside of the Milky Way. It's not galaxies. But certainly, it would make my job a lot sadder because we'd see a lot fewer galaxies as we started to have the redshift horizon change, or let me think. The farthest distance of the universe we can see that light has had time to travel to us will have changed.
So in those 5 death scenarios that you outlined, which one of them would produce the most detectable LEGO gravity waves?
Mergers. The reason is because not only are the galaxies merging, their black holes are merging. So at Caltech, there's a program that is actually looking at pulsars being rapidly spinning neutron stars, that are actually using timing of pulsars across the sky to create basically this mega telescope looking for gravitational waves that actually come out of these supermassive black holes merging. There are probably other things I'm not thinking of, but that is one that I know is actively being studied right now, is can we see 2 black holes smushed together in a merger?
Young guy in the back again. You. That's you. Go ahead.
Would it be easy to track hydrogen by using the rare tritium isotope? Like the radiation?
Yes, I will. Again, partially because I have to think about it. The question was, would we be able to track hydrogen using tritium isotope, which I think in this case is 1 proton and 2 neutrons? It would be very tough, partially because tritium is even rarer than deuterium, and deuterium is extremely rare. In radio astronomy, we're actually starting to look into ways to use ALMA, which was one of these radio dishes, to study the hydrogen deuterium molecule. Because again, that is a direct measure of the H2, whereas carbon monoxide is just a proxy. It's assuming we know what the abundance is going to be of the hydrogen versus the carbon monoxide, but the carbon monoxide is 1/10,000th the abundance of H2, and the H2 is what the stars are forming out of. So it's a really good question, and it is actually onto something that astronomers are thinking about, but we tend to stick to the less rare deuterium when we're thinking about that. Yeah, it's very unlikely. I can't think of anything astronomically where we've measured tritium. We've definitely measured deuterium.
Can you explain why it's necessary to have a hydrogen molecule to initiate star formation?
I can. That is because of the conditions you're looking for to form stars. When you're forming a star, you need to be able to smush gas close enough together that it collapses gravitationally. That means you need to look for places that the gas is cold and the gas is dense. And it turns out, chemically, the places that the gas is sufficiently cold and sufficiently dense are places where the hydrogen is naturally in its molecular form. So there's plenty of H1 being atomic hydrogen, but that is not where we're seeing stars form. Okay, so let me see if I can rephrase the question. String theorists and people who are looking, for instance, to unify all of the theories of force, from the electromagnetic force to the weak force to the gravitational force to the strong force, and the weak and the strong force act on nuclei, are one of the manifestations of some of the ways that the math seems to work out, is that there are things like folded universes and multi-universes, and whether or not we've seen any evidence of this in astronomy. And my answer to that is we haven't seen evidence of it, but we haven't not seen evidence of it. It's kind of one of those things that's still beyond, I think we would say, beyond, like if I were writing a paper on this, I'd say beyond the scope of this paper. Correct. Yeah, so people are working on theories of things like modified gravity to see if general relativity, like playing with general relativity, can actually explain the dark energy results that we have seen. Mark Phillips, I think, was here for the very first one and probably talked about supernovae showing that the universe is accelerating. And people have been playing with not just ideas of this mysterious dark energy because we don't know what it is, but also looking at modifying the fundamental equations of gravity so that it isn't quite so, I'm trying to think of the word I'm like, linear is kind of the word, but it doesn't need a unit. So it gives you some units that it can act over. And I guess the joke of observers is the second we give theorists new data, theorists will figure out a way to fold their equations in so that their equations predicted the data that we give them.
One last question.
String theory has been mentioned. String theory has multiple dimensions, like 11. Is it possible that dark energy and dark matter are aspects of the universe which are in other dimensional sets we're observing?
It's possible. Data, again, it's the same answer as before. Our observations don't rule it out, and our observations don't confirm it. Indeed. So right now, it's a lot of the work in string theory and other things is actually making the math equations work out, and that's what Albert Einstein was doing, and he predicted general relativity and the precession of Mercury. So sometimes it works out. We just are not in a place in astronomy yet where we can do these kinds of tests. I will point out, though, that general relativity was very well confirmed by the LIGO result of gravitational waves. That like the models fit perfectly because that's exactly what general relativity said they would see.